Halley's Comet or Comet Halley, officially designated 1P Halley, is a short-period comet visible from Earth every 75–76 years. Halley is the only known short-period comet that is clearly visible to the naked eye from Earth, and the only naked-eye comet that might appear twice in a human lifetime. Halley last appeared in the inner parts of the Solar System in 1986 and will next appear in mid-2061. Halley's returns to the inner Solar System have been observed and recorded by astronomers since at least 240 BC. Clear records of the comet's appearances were made by Chinese, Babylonian, and medieval European chroniclers, but were not recognized as reappearances of the same object at the time. The comet's periodicity was first determined in 1705 by English astronomer Edmund Halley, after whom it is now named. During its 1986 apparition, Halley's comet became the first comet to be observed in detail by spacecraft, providing the first observational data on the structure of a comet nucleus and the mechanism of coma and tail formation. These observations supported a number of long-standing hypotheses about comet construction, particularly Fred Whipple's dirty snowball model, which correctly predicted that Halley would be composed of a mixture of volatile ices, such as water, carbon dioxide, and ammonia, and dust. The missions also provided data that substantially reformed and reconfigured these ideas. For instance, now it is understood that the surface of Halley is largely composed of dusty, non-volatile materials, and that only a small portion of it is icy. Pronunciation: Comet Halley is commonly pronounced Haley, rhyming with valley, or Healy, rhyming with daily. Speakings of Edmund Halley's name during his lifetime included Haley, 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 Halley, Hawley, and Hawley, so its contemporary pronunciation is uncertain. Computation of orbit: Halley was the first comet to be recognized as periodic. Until the Renaissance, the philosophical consensus on the nature of comets, promoted by Aristotle, was that they were disturbances in Earth's atmosphere. The idea was disproved in 1577 by Tycho Brahe, who used parallax measurements to show that comets must lie beyond the Moon. Many were still unconvinced that comets orbited the Sun, and assumed instead that they must follow straight paths through the Solar System. In 1687, Sir Isaac Newton published his Principia, in which he outlined his laws of gravity and motion. His work on comets was decidedly incomplete. Although he had suspected that two comets that had appeared in succession in 1680 and 1681 were the same comet before and after passing behind the Sun, he was unable to completely reconcile comets into his model. Ultimately, it was Newton's friend, editor and publisher, Edmund Halley, who, in his 1705 synopsis of the astronomy of comets, used Newton's new laws to calculate the gravitational effects of Jupiter and Saturn on cometary orbits. This calculation enabled him, after examining historical records, to determine that the orbital elements of a second comet that had appeared in 1682 were nearly the same as those of two comets that had appeared in 1531 and 1607. Halley thus concluded that all three comets were, in fact, the same object returning every 76 years, a period that has since been amended to every 75–76 years. After a rough estimate of the perturbations the comet would sustain from the gravitational attraction of the planets, he predicted its return for 1758. Halley's prediction of the comet's return proved to be correct, although it was not seen until the 25th of December 1758 by Johann Georg Pallich, a German farmer and amateur astronomer. It did not pass through its perihelion until the 13th of March 1759, the attraction of Jupiter and Saturn having caused a retardation of 618 days. This effect was computed prior to its return by a team of three French mathematicians, Alexis Clairaut, Joseph Lalande, and Nicole Raine-Lepaute. Halley did not live to see the comet return, as he died in 1742. The confirmation of the comet's return was the first time anything other than planets had been shown to orbit the Sun. It was also one of the earliest successful tests of Newtonian physics, and a clear demonstration of its explanatory power. The comet was first named in Halley's honor by French astronomer Nicolas Louis de Lacaille in 1759. The possibility has been raised that first-century Jewish astronomers already had recognized Halley's comet as periodic. This theory notes a passage in the Talmud that refers to a star which appears once in 70 years that makes the captains of the ships orbit and origin. Halley's orbital period over the last 3 centuries has been between 75–76 years, although it has varied between 74 to 79 years since 240 BC. Its orbit around the Sun is highly elliptical, with an orbital eccentricity of 0.967. The perihelion, the point in the comet's orbit when it is nearest the Sun, is just 0.6 astronomical units. This is between the orbits of Mercury and Venus. Its aphelion, or farthest distance from the Sun, is 35 astronomical units. Unusual for an object in the Solar System, Halley's orbit is retrograde. It orbits the Sun in the opposite direction to the planets, or clockwise from above the Sun's north pole. The orbit is inclined by 18 degrees to the ecliptic, with much of it lying south of the ecliptic. Due to the retrograde orbit, it has one of the highest velocities relative to the Earth of any object in the Solar System. The 1910 passage was at a relative velocity of 70.56 km per second. Because its orbit comes close to Earth's in 2 places, Halley is the parent body of 2 meteor showers, the Eta Aquariids in early May, and the Orionids in late October. Observations conducted around the time of Halley's appearance in 1986, however, suggest that the Eta Aquarid meteor shower might not originate from Halley's comet, although it might be perturbed by it. Halley is classified as a periodic or short-period comet, one with an orbit lasting 200 years or less. This contrasts it with long-period comets, whose orbits last for thousands of years. Periodic comets have an average inclination to the ecliptic of only 10 degrees, and an orbital period of just 6.5 years. So Halley's orbit is atypical. Most short-period comets are called Jupiter family comets. Those resembling Halley, with orbital periods of between 20 to 200 years and inclinations extending from 0 to more than 90 degrees, are called Halley-type comets. To date, only 54 Halley-type comets have been observed, compared with nearly 400 identified Jupiter family comets. The orbits of the Halley-type comets suggest that they were originally long-period comets whose orbits were perturbed by the gravity of the giant planets and directed into the inner solar system. If Halley was once a long-period comet, it is likely to have originated in the Oort cloud, a sphere of cometary bodies that has an inner edge of 20,000 to 50,000 astronomical units. Conversely, the Jupiter family comets are believed to originate in the Kuiper belt, a flat disk of icy debris between 30 astronomical units and 50 astronomical units from the Sun. Another point of origin for the Halley-type comets has been proposed. In 2008, a trans-Neptunian object with a retrograde orbit similar to Halley's was discovered, 2008 KV42, whose orbit takes it from just outside that of Uranus to twice the distance of Pluto. It may be a member of a new population of small solar system bodies that serves as the source of Halley-type comets. Halley has probably been in its current orbit for 16,000–200,000 years, although it is not possible to numerically integrate its orbit for more than a few tens of apparitions, and close approaches before 837 AD can only be verified from recorded observations. The non-gravitational effects can be crucial. As Halley approaches the Sun, it expels jets of sublimating gas from its surface, which knock it very slightly off its orbital path. These orbital changes caused delays in its perihelion of 4 days, average. In 1989, Boris Chirikov and Vitaly Vyacheslawov performed an analysis of 46 apparitions of Halley's Comet taken from historical records and computer simulations. These studies showed that its dynamics were chaotic and unpredictable on long timescales. Halley's projected lifetime could be as long as 10 million years. More recent work suggests that Halley will evaporate, or split in two, within the next few tens of thousands of years, or will be ejected from the Solar System within a few 100,000 years. Observations by D.W. Hughes suggest that Halley's nucleus has been reduced in mass by 80 to 90% over the last 2,000 to 3,000 revolutions. Structure and composition. The Giotto and Vega missions gave planetary scientists their first view of Halley's surface and structure. Like all comets, as Halley nears the Sun, its volatile compounds begin to sublime from the surface of its nucleus. This causes the comet to develop a coma, or atmosphere, up to 100,000 kilometers across. Evaporation of this dirty ice releases dust particles, which travel with the gas away from the nucleus. Gas molecules in the coma absorb solar light and then re-radiate it at different wavelengths, a phenomenon known as fluorescence, whereas dust particles scatter the solar light. Both processes are responsible for making the coma visible. As a fraction of the gas, molecules in the coma are ionized by the solar ultraviolet radiation pressure from the solar wind. A stream of charged particles emitted by the Sun pulls the coma's ions out into a long tail, which may extend more than 100 million kilometers into space. Changes in the flow of the solar wind can cause disconnection events, in which the tail completely breaks off from the nucleus. Despite the vast size of its coma, Halley's nucleus is relatively small, barely 15 kilometers long, 8 kilometers wide and perhaps 8 kilometers thick. Its shape vaguely resembles that of a peanut. Its mass is relatively low and its average density is about 0.6 grams per cc, indicating that it is made of a large number of small pieces, held together very loosely, forming a structure known as a rubble pile. Ground-based observations of coma brightness suggested that Halley's rotation period was about 7.4 days. Images taken by the various spacecraft, along with observations of the jets and shell, suggested a period of 52 hours. Given the irregular shape of the nucleus, Halley's rotation is likely to be complex. Although only 25% of Halley's surface was imaged in detail during the flyby missions, the images revealed an extremely varied topography, with hills, mountains, ridges, depressions, and at least one crater. Halley is the most active of all the periodic comets, with others, such as Comet Encke and Comet Holmes, being 1 or 2 orders of magnitude less active. Its day side is far more active than the night side. Spacecraft observations showed that the gases ejected from the nucleus were 80% water vapor, 17% carbon monoxide and 3 to 4% carbon dioxide, with traces of hydrocarbons, although more recent sources give a value of 10% for carbon monoxide and also include traces of methane and ammonia. The dust particles were found to be primarily a mixture of carbon, hydrogen, oxygen, nitrogen compounds common in the outer solar system, and silicates, such as are found in terrestrial rocks. The dust particles decreased in size down to the limits of detection. The ratio of deuterium to hydrogen in the water released by Halley was initially thought to be similar to that found in Earth's ocean water, suggesting that Halley-type comets may have delivered water to Earth in the distant past. Subsequent observations showed Halley's deuterium ratio to be far higher than that found in Earth's oceans, making such comets unlikely sources for Earth's water. Giotto provided the first evidence in support of Fred Whipple's dirty snowball hypothesis for comet construction. Whipple postulated that comets are icy objects warmed by the Sun as they approach the inner solar system. causing ices on their surfaces to sublimate, and jets of volatile material to burst upward, creating the coma. Giotto showed that this model was broadly correct, though with modifications. Halley's albedo, for instance, is about 4%, meaning that it reflects only 4% of the sunlight hitting it, about what one would expect for coal. Thus, despite her appearing brilliant white to observers on Earth, Halley's comet is in fact pitch black. The surface temperature of evaporating, dirty ice ranges from 170 K at higher albedo to 220 K at low albedo. Vega 1 found Halley's surface temperature to be in the range 300 to 400 K. This suggested that only 10% of Halley's surface was active, and that large portions of it were coated in a layer of dark dust that retained heat. Together, these observations suggested that Halley was in fact predominantly composed of non-volatile materials, and thus more closely resembled a snowy dirt ball than a dirty snowball.